Welcome back. This is Mr. Hassan's Maths channel. I'm answering now question number 9 from the October 2017 Core Mathematics C34 paper from the Edexcel International A-Level exam. I'm answering this question upon the request of some of the students, and there's a particular part of this question which is quite relevant to the type of questions that do appear in some of the new style P3 papers. So that's one of the reasons. This is actually a P3 kind of part of this old specification. C34 used to be like the P3 and the P4 kind of combined into one exam. So this is actually relevant to P3, this question. So anyway, so it says here, f of x is equal to 2 ln of x minus 4. X is greater than 0, which it has to be because you can have 0 or negative input for the ln function. And so x is the member of the real numbers, but positive values. X is greater than 0. So part A is about sketching the curve with the equation first y equals f of x, and then y equals the modulus of f of x, where the f of x is inside the modulus sign. On each diagram, show the coordinates of each point at which the curve meets or cuts the axes, and on each diagram state the equation of the asymptote. Okay, so for part 1, it's just the basic curve y equals f of x. So we have here a ln function, and it's been transformed slightly. Okay, so what we'll do is we will draw a pair of axes. Okay, so you have your y-axis and you have your x-axis. Now, if we were to draw, for example, y equals just ln x on its own, the graph of y equals ln x is the inverse of y equals e to the power of x. So it basically has a range which is infinite, but its domain is only for x values greater than 0, and it goes through the point 1, 0. Okay, because when y equals 0, you get ln x equals 0. This means log to the base e of x equals 0. That means e to the power of 0 equals x. So x is equal to 1. Anything to the power of 0 is 1. So it's going to be a graph that looks something like this. It goes something like that. That's y equals ln x. Okay. Now, there's a couple of transformations that have taken place. One of them is a vertical stretch of factor 2, which causes the graph to basically be a bit more stretched out. So the points are all like this point is twice, this point, the y value has been multiplied by 2. So it's twice as far from the x-axis as the original point. And then what's happened is minus 4. So it's now been, everything has dropped by 4 units. Okay. So it's not going to go through at 1, 0 anymore. It's going to go through somewhere else. But the vertical asymptote is still going to be the same. The vertical asymptote is still going to be exactly the same because these do not change any of the x coordinates. So the line x equals 0 was the asymptote of the original graph. So the line x equals 0 is going to be the asymptote of the, asymptote of this graph. Okay, x equals 0. And the graph is going to look something like this. Now, where's that point going to be? Let's just calculate it now. So we can see it's never going to touch the y-axis. Okay. So now let's try to figure out where does this graph cross the x-axis. Now, it crosses the x-axis when y equals 0. So just the same way we worked out for ln x, we'll do the same thing. We have 2 times ln x minus 4 equals 0. So 2 times ln x is equal to 4. So ln x is equal to 4 divided by 2, which is 2. So you're going to have log, with this basically means log to the base e of x equals 2, which means x is equal to e squared. So x is going to be, the coordinates of the place where it hits the y-axis is going to be e squared. Okay, so the coordinates is e squared 0, you could say. So it's going to be a graph that looks something like this. Have that type of shape. This is y equals f of x. Okay, that's the asymptote. That's where it hits the x-axis. It never touches the y-axis. And there is the graph. Now, if you want to draw y equals the modulus of f of x, then it will be almost identical to this. So I'm going to actually just copy this. Let me copy all of this. And I'm going to paste it down here. Okay, except what happens when you have the modulus, anything above the x-axis stays as it is. Anything below the x-axis is reflected in the x-axis. So it's going to be looking like this. Okay, so this part is going to reflect in the x-axis. All right, and it's going to look something like this. And what's below the x-axis is going to be erased. So it will still hit the x-axis in exactly the same place, but it won't go all underneath the x-axis. It will always be positive, and the asymptote will still be x equals 0. So basically, you know, the points are the same. The asymptote is the same, okay, but the you could say the graph is different because anything below the x-axis has been reflected in the x-axis. So there's a graph of y equals a modulus of f of x. Okay, so that's question A done, part 1 and 2. So accordance to each point with yes, all done. Right. Now for part B. It says find the exact solutions for the modulus of f of x equals 4. Okay, so if we take that same graph, actually we can do that here. What I'll do is I'll take the graph in a slightly different way. I'll take this graph as a picture. Paste it over here. Make it a bit too big right now. Okay, so we can just visualize what we're doing. I like to always visualize what's happening. We don't have to do this, but it does help to make things easier. So we want to solve the equation where f of x is equal to 4. Now 4 is going to be somewhere over here. That's the line y equals 4. Okay, that's the line y equals 4. Let's just make that solid and do a color. So that's the line y equals 4. So we can see that this has two solutions. Okay, this equation is going to have two solutions. All right. So we got the modulus of f of x, which is the modulus of 2 times ln of x minus 4 is equal to 4. So basically what we can say is, algebraically we can answer this by saying that means the 2 times ln of x minus 4 is either equal to 4 or 2 times ln x minus 4 is equal to negative 4. Okay, so those are the two, you know, possible ways of solving this. You know, either this or that. Okay, graphically, what we can say is this is the point where this is basically the positive argument of the function, the modulus function. This is the when you just leave everything as it is. So you just put, this is going to be y equals 2 times ln x minus 4. And this would be the negative argument where you change the sign of everything inside the modulus sign. So this would be 4 minus 2 ln of x. It's like they change signs. Okay. So basically, this is the same as this basically. If I say 4 minus 2 ln x equals 4, okay, 4 minus 2 ln x equals 4. It's the same as saying this. If I change that to a minus and I change the sign of these two, it's the same thing. So thinking about it this way is the algebraic way. Thinking about it this way is graphic. They'll give you the same answer. So here we're going to add 4 to both sides. So we have 2 ln x equals 8. And then we divide both sides by 2. So ln x equals 4. So we can say, you know, e to the power 4 equals x. So x equals e to the power 4. You can rewrite this in index form. Okay. And over here, we're going to add 4 to both sides. We'll end up with 2 times ln x equals 0. So ln x equals 0. And of course, that's e to the power of 0 equals x. So x equals e to the power of 0. So x equals 1. So those are the exact solutions to this equation. You have x equals e to the power of 4 and x equals 1. Okay, so that would be 1 and that would be e to the power of 4. Those are the solutions, the exact solutions to the equation, the modulus of f of x equals 4. Okay, and we can put this in here and we can basically check to see the right answers. So if I put e to the power of 4 in here, I have 2 ln of e to the power of 4 minus 4. Now we know e to the power of 4 is going to be like, if you rewrite this, you can use the power law. That's going to be 4 times 2, which is 8 times ln e minus 4. And ln e equals 1, so 8 minus 4 is equal to 4. And we can see them. This becomes 4, and this is equal to 4. The modulus 4 is equal to 4. That works. And if you put 1 instead of the x, you have 2 times ln of 1 minus 4. And ln of 1 is 0, so you end up with minus 4. So the modulus of minus 4 is equal to 4. That also works. So both of those give us correct solutions. We can check that. We can see that from our graph as well. Okay, so there's the answer to part B. Now for part C. And C and D is really the question that students were asking about. Okay, so it says find g of f of x, giving your answer in its simplest form. So g of f of x means you're going to take the function g and its input is going to be the function f. So x goes into f, which gives us this, and then f of x goes into g. And this is g. So we're going to basically find g of 2 ln x minus 4, which means that x here is replaced by 2 ln x minus 4. So you have e to the power of, instead of x, I'm going to put 2 ln x minus 4. Okay, and then I'm going to have plus 5. Okay, so the x here has been replaced by 2 ln x minus 4. Then I've got the minus 2 here at the end. So this is going to be e to the power of 2 ln x minus or plus 1 minus 2. Okay, so now we have to give the answer in its simplest form. All right, so what I can do here is I can rewrite this as e to the power of 2 ln x times e to the power of 1 minus 2, which is the same as e to the power of ln of x squared using the power law times e to the power of 1 minus 2. Now what happens here is you have e to the power of ln of x squared. This is like e and ln x are inverse of each other. They cancel each other out. So it's like having f and the inverse of f of x. They cancel each other out, leaving you just with the x. So what we're going to be left with here is just x squared. So this is going to become x squared e minus 2. So that is g of f of x. Okay, this cancels out. Okay, e ln of something is going to be just that thing, x. Okay, because they are inverses. Right? That's how we can understand what that is. If you want to understand that in a different way, we can say, okay, let's call e ln x, let's call it y. Right? We want to get rid of this ln x. So what we want to get rid of this e. So what we can do is, if we take the ln of both sides, let's say we take the ln of both sides. So we say ln of e to the power of ln x is equal to ln of y. So now you have ln x times ln e equals ln y. Ln e is equal to 1, so you have ln x equals y, so y equals x. You can see that this is going to be the same as just x. Okay, so the inverse composite with the original function, they cancel each other out. That's how you can understand it in the more simpler way. So there's the answer for g of f of x. And then for part D. And now for part D, and here we're told, hence or otherwise state the range of g of f. Okay, so if we use the hence method, okay, then we're going to use this result. G of f of x is equal to x squared e minus 2. Now e is just a constant. Okay, e is the natural number. Okay, and the value of e, if you forget what it is, you can find it in your calculator. It's basically can be found by pressing alpha and this button here. It's 2.7. It's just a constant, kind of like pi. So this is basically a quadratic, which is ex squared minus 2, you could say. 2.7, whatever, x squared minus 2. All right, so the function g of f of x is basically a quadratic function. Right? But however, we have to consider what the input of this function can be. Now we know that if you have g of f of x, the x goes into f. Now x can only be values which are greater than 0. Okay, so that's the domain of f. X is greater than 0. And the domain of g, okay, the domain of g basically can be all real numbers. Okay, can be all real numbers. All right, so the output of f is the input of g. Okay, and what is the output of f? Well, the output of f is all real numbers as well. Okay, so the range of f is all real numbers. Okay, so what can go into g, okay, is all real numbers. Okay, you can take all real numbers. The output of f is all real numbers, but the input of f can only be values of x greater than 0. Right? So basically what you can't do is you can't put values of x less than 0 into here. Okay, which means the input of g must also be following on from that. So what we can say is that the domain of g of f of x, must be values of x which are greater than 0, because that's like what's common between f and g. That's what's common between them. Okay, so what can go into f is only values of x greater than 0. Okay, so because you can't put inside here values of x less than 0, okay, that means the domain of this has to be x is greater than 0. Okay, so when you think about the graph of this would be like a quadratic graph, which will have this type of shape. Okay, and it will cut through the y-axis. This is like one where the line of symmetry is basically the y-axis. Okay, because if you think about the vertex is going to be 0, minus 2. However, there are no negative inputs for x because you can't put any values of x less than 0 or less. So this is going to start from here, and it's going to not include this, this point itself. X equals 0 can't be included, and it's going to go like this, and it's going to have this type of shape. So we can see the range of this function starts from just above minus 2, and it goes on forever upwards. So we can say the range is y is greater than negative 2, not equal to. Okay, because if you put x equals 0 into this function, it's undefined. Okay, and because this is a composite function made up of that, you can't put values in the beginning into function f, which will cause it to be undefined. That's the problem there. Right? So even though the output of f of x is infinite, right, its input has to be x values greater than 0. Therefore, you can't put x values less than 0 into the whole function. That's how you can think about it. Okay, the otherwise way of thinking about it might be a bit clearer in terms of how to think that basically its output will be all real values. Okay, if you put x values greater than 0 into here, it's going to have this kind of shape as we drew earlier. Okay, that's going to go up forever, down forever. So we can say that the f of x, its output is is basically all real values. Okay, its range is all real values. Okay, and if you put all real values into here, okay, e to the power of x plus 5 minus 2, well, let's just think about e to the power of x. E to the power of x looks like this. It goes through 0, 1. Okay, e to the power of x plus 5. X plus 5 is just a translation of some units, horizontally. Okay, so it won't affect the asymptote here. It won't affect this value over here. Okay, so when y is equal to 0, when x is equal to 0, you'll have e to the power of 5 minus 2. So after this transformation, it will be e to the power of 5, okay, minus 2. And then when you take away 2 from this whole thing is going to go down 2 units. The asymptote will move down 2 units. The asymptote will go from 0 down to y equals negative 2. So this will be moved down. This will be e to the power of 5 minus 2. And then you're going to go down by another 2 units. It will be e to the power of 5 minus 4. So it's going to look something like this. Right, and we can see that this is an asymptote y equals minus 2. So this graph will always be above y equals minus 2. So we can see from here that the range of f of g is going to be greater than minus 2, not equal to it, because that's an asymptote. So we can think this is the otherwise way of doing it, where you consider the output of f of x, okay, and you think about what happens when that goes into g of x. Output of f of x is all real numbers, okay, because if you put any value of x into here, which is greater than 0, it was going to be defined, and it's going to be, the output can be anything from negative infinity to positive infinity. And if you put anything between negative infinity to positive infinity into here, its output will always be greater than minus 2. This is like e to the power of something minus 2. The asymptote is only affected here by the minus 2, so it goes from 0 to minus 2. As we know, e to the power of x has an asymptote, y equals 0. Now the asymptote is y equals minus 2. So its range will be everything greater than minus 2. Right, so there's 2 ways of dealing with this question. Very important there. A point here for the for this question. Now, other questions from this particular paper can be found in the playlist that will appear on the top of the screen. At the end of the video, other questions from the topic of functions, like inverse functions and composite functions and so on, in the playlist over here. Modulus functions you find over here. And you can subscribe to the channel by clicking on this link. Thank you for watching, and see you soon.